All right, we're going to talk a little bit about minerals today. Start off with a little basic atomic structure. I think most everybody knows here we've got the nucleus. Inside the nucleus we've got neutrons, which have a neutral or no charge. We have protons, which have a positive charge. And then surrounding the nucleus we have layers or shells of electrons that have negative charges. In order to have a stable element, the number of negative electrons has to be equal to the number of positive protons that are in the middle. We take a look at the periodic table for a second. We're not going to do a lot with this, but the two most important elements, at least to us at this point, are going to be silicon and oxygen. Right? When silicon and oxygen bond together, it creates what's called a silicate mineral, and the silicates make up the majority of the crust that we walk on. When we put them together, we end up what's called the silica tetrahedron. All right, so we have one small silicon in the middle, and then we have surrounding that 4 oxygens. And those 4 oxygens are in the shape of what's called a tetrahedron, which is a pyramid, 4-sided pyramid made up of triangles. So it's kind of, you see on the right, the little pyramid on the right there. All right. This structure and variations of it make up about 95% of the Earth's crust by volume. All right. Silicon takes up a lot of space. They're very large, and so they take up a lot of the space. So the most important grouping of minerals that we deal with are going to be the silicates. Okay. All right, from the front page of your reference table, you can see we have crust, hydrosphere, and troposphere. So land, sea, and air, so to speak. All right? And then we've got some elements on the side here, and you can see that they separate out crust by mass and volume. Right? Oxygen, doesn't matter which one we're looking at, oxygen takes up the most percent, and 94% by volume, 46% by mass. Okay. Silicon, not very much by volume, a lot by mass. If you add them up by mass, we're looking at 75% by mass and almost 95% by volume. So silicon and oxygen, 2 extremely important. All right. See it there, see it there. All right, some silicate examples. You don't need to know the structure they take on, but olivine, pyroxene, amphibole, talc, mica, quartz, garnet, and feldspar, those are all silicate minerals that are on your reference tables. Stilbite and beryl are not on your reference tables, but you can see that they become increasingly complex as you merge those tetrahedrons together. Whether you have a single one or you have a big framework of them, the more you have, the more complex the structure is, and it changes the mineral that you're dealing with. All right, so what is a mineral? Well, a mineral has to fulfill 5 criteria. 1, it's got to be naturally occurring. It can't come from anything that was ever living. It has to be a solid. It has to have a chemical formula. And the atoms have to be arranged in a repeating structural pattern of some sort. If it doesn't fit these 5 things, then we're not talking about a mineral. Okay, it's something else. All right, so page 16. We look at page 16 in the reference table. Right there, that gives you pretty much all the information that you're going to ever need to deal with on minerals. So if you look at the top, we can talk about categorizing them by luster, hardness, how they break, some common colors they come in, some different characteristics of each, how we use them, what is the chemical composition, and what is the name. Okay. All right, so how do we form minerals? Well, we form them a couple different ways. One, we can cool down some molten material, molten rock, lava or magma. And when we do that, minerals crystallize. Whatever elements make up the lava is what you're going to get when it crystallizes. Right. Second type is we can create what are called evaporites. If you have a solution and water evaporates away from that solution, that leaves behind those minerals. I use that example of the salt potato. If you're cooking salt potatoes for barbecue and you throw them in there, you dump the salt in, you boil the crap out of it for 20 minutes. When you're all done, pretty much all the water's gone, and you got this white crusty stuff all over the pan. That's salt that's left behind. That's an evaporite. Right? And then finally, same thing, working with a water solution, but now the water doesn't evaporate away. What we have here is if we have an oversaturated solution, if we put too many minerals, too much mineral material in the water can only hold so much. It won't dissolve anymore, and then it falls to the bottom. It settles out, and we call that a precipitate. Okay? All right, so how do we identify minerals? We look at properties. We look at their properties, the physical properties, chemical properties, and some of them have some cool special properties that we talked about. All right, let's look at the physical properties first. First property, color. We're doing this first because it's not really the most important property. We're going to try to get out of the way here. Color is, what does it look like? What is the, I mean, you pick it up, that's the color. Everybody knows what the color is. The problem with color is that it's not a good way to identify a mineral. Okay? A couple of them, yeah, it's okay. You know, sulfur, when you look at sulfur, everybody kind of knows what sulfur looks like when you pick up a piece of sulfur. There's this other mineral called malachite. Pretty much that's the only mineral that looks like that. But other than those couple, pretty much anything that we're going to run into, they might look very similar. So you could pick up two minerals and they might look identical. They might all have the same color, but they might be completely different minerals. In this instance, the examples I used, you know, talc, quartz, and calcite, even though the examples don't look exactly alike, talc, quartz, and calcite all can look very similar to each other. They can all come in white, and they can all look very similar, so when you pick them up, you might not be able to distinguish them based on just color. So we can use kind of color to help us with other things, but we don't want to just use color to identify the mineral that we're talking about. And not to mention the fact that there are some minerals, for example, quartz, that basically can come in pretty much any color you can think of. I put, you know, 5 of them, the key main ones that they come in here. You know, purple amethyst, we have white, clear, smoky, rose quartz. Hematite can be red, brown, it can be silver. But again, you might see a particular mineral and it could be multiple different colors. So if you go by just the fact that, oh, well, quartz is clear, you know, it's got to be quartz. No, because you could have a piece of purple quartz, you could have a piece of rose quartz, you could have a piece of white quartz, whatever, okay? So you guys, so color is not great to use by itself. In fact, it's pretty bad to use by itself. All right, next physical property is streak. This is when you take the mineral and you grind it on a streak plate, a porcelain plate. All right, it's what the color is once you've powdered it, once you've ground it up. And this is pretty reliable, okay? Because some minerals look very different once you grind them up. Pyrite is a big example. Pyrite looks like gold. Some samples of pyrite you cannot distinguish from gold. But if you take gold and rub gold on a porcelain plate, on a streak plate, it looks gold. But if you rub pyrite on a streak plate, it looks dark gray or black. So it's very, very different. All right, luster. How does it reflect light? How does it shine? And we have 2 basic lusters. We have metallic luster, if the mineral looks like a shiny metal. And then we have the non-metallic luster if it doesn't, if it's dull, if it's glassy, if it's earthy, whatever. Okay, it doesn't look like metal. It can look like glass, that's different. But it can't look like a piece of metal, you know, silver, gold, copper, whatever. Okay? Hardness. If a mineral is very hard, that means it's very difficult to scratch that mineral. If it's very soft, that means it's very easy to scratch that mineral. All right? And we measure hardness on what's called the Mohs hardness scale. It ranges from a 1, which is the softest a mineral can be, and the example I give you here is talc. Talc is a 1, all the way up to the hardest that a mineral could be, The most difficult to scratch is a diamond, which is 10. Now, I know there's no diamonds on our reference table. Okay? If you look at the reference tables, all right, the hardest mineral we have is garnet, which could potentially be a 7.5. All right? But they have they've picked 10 key minerals that they use as reference minerals. All right? These are the standard 10 minerals that go on a hardness scale. All right? Talc, gypsum, calcite, fluorite, apatite, feldspar, quartz, topaz, corundum, and diamond. If you have those 10 samples, then whatever's given to you, you can compare it to those. All right? If something is harder than the mineral you have, you're not gonna be able to scratch it. If it's softer, you're gonna be able to scratch it. All right? And the field scale that we use is a piece of glass plate. Okay? Glass has a hardness of about a 5.5. So if you can scratch glass with the mineral, it's harder than 5.5. If you can't scratch the glass, that means it's softer than 5.5. All right, breakage. Okay, how does the mineral split when you hit it, like with a hammer? All right. If you can find any, even small, nice flat planes, nice flat surfaces, we say the mineral exhibits cleavage. If when we hit it, it's either wavy or bumpy or uneven or jagged in any way, we say it has fracture. We have to be able to find a nice a nice flat surface, even if it's small, in order to say it has cleavage. All right. So now, all these physical properties we talked about, they're all determined by the structure inside, the mineral structure, the atomic structure, how it's bonded together. All right. That's going to give us a determination of how hard the mineral is. For example, diamond is carbon, so is graphite, but diamond is very hard, graphite's very soft. It's how it's bonded inside. If it has very weak bonds, they're going to break easily, and it's a soft mineral like graphite. If they're bonded very strongly to each other, it's going to be a very hard mineral like diamond. All right. All right, one chemical property that we're going to talk about is effervescence or fizzing or bubbling. All right. Calcite, the mineral calcite, calcium carbonate, reacts with hydrochloric acid. We have the formula below here, calcium carbonate plus 2 hydrochloric acids yields calcium chloride plus water plus carbon dioxide. You don't need to know the formula. What you need to know is when you see the bubbling, that's the calcite turning into calcium chloride and water, and then it's giving off the carbon dioxide gas, and that's what's bubbling. All right. So calcite bubbles in acid. Dolomite does bubble, but you have to grind it up into a powder first to get to bubble really well. Otherwise, it doesn't do a lot. But the mineral calcite makes up the sedimentary rock limestone. Limestone will react to acid. All right. Limestone can be metamorphosed into marble. Marble also, and we'll talk about the rocks a little bit later, but the rock marble will also effervesce or fizz in acid. Okay. And just a couple of cool special properties. Lodestone is magnetic. It's a form of the mineral magnetite. Isolin spar, which is a very special type of calcite, very nice, good-looking piece of calcite. It splits the image as you look through it into 2 images. It refracts the light and splits the image into 2 images, so you see 2 of them. Pitch blende is radioactive. Obviously, you can't show you one of those samples. I don't want to give you cancer. And finally, we have some glowing properties. All right. Some minerals absorb energy and release that energy back in the form of glowing. It glows. And there's a couple different types. Fluorescence is where it releases the energy very quickly and it only glows for a second after you take the energy source away. And phosphorescence, which is something that can absorb the energy, and then once you take the energy source away, it will continue to glow for several seconds, several minutes, whatever, for a while. It'll release the energy a lot slower and hold on to it a lot longer. Okay?